while doing water treatment and even the treatment of chemical and biological wastes, we always meet the concept of determining the pH of that solution available in the lab. So in this discussion, we'll be looking at the pH of a solution that is given to us and given its acid dissociation constant. So the guiding question says, what is the pH of a 0.75 molar of ethanoic acid solution given the acid dissociation constant of 1.8 times 10 to the power negative 5? So let's look at the dissociation of this weak acid. So this is ethanoic acid dissociating to give ethanoate ions and some hydrogen ions. So another one would say you get ethanoic acid, dissolve it in water, and this would form ethanoate ions plus hydronium ion. All of this is still the same. Now what you are going to be using is ICE. We want to look at initially what is the concentration of hydrogen ions. When the reaction has taken place or when the dissociation has occurred, what is the change in the concentration? And then at equilibrium, what is the concentration? So initially we have 0.75 molar and then we have 0 of this because it hasn't dissociated. And then after dissociation, we are going to assume that we formed X moles of hydrogen ions and then X moles of ethanoate ions, meaning here the difference or the change is going to be negative X, because if the change here is X and the change here is X, it means we are reducing the concentration of ethanoic acid. Initially it is 0.75, so it has to reduce so that we form hydrogen ions somewhere. So it will reduce by negative X. So at equilibrium, we just add the initial concentration plus the change in concentration. This becomes 0.75 minus X. This is X. So we have to write down the acid dissociation constant Ka, which is going to be the concentration of the products. That is the concentration of ethanoate ions times the concentration of hydronium ions divided by the concentration of ethanoic acid. And this is going to give us, we know Ka, we know these values. So at equilibrium, we are taking the value for this, that will be X. All of these are raised to a power 1 because the stoichiometric factors here is 1, 1, and 1 there. Water doesn't take place. Just be reminded that liquids and solids do not take part in the equations at equilibrium. So this is times X divided by, at equilibrium, ethanoic acid is 0.75 minus X. So this is going to be 1.8 times 10 power negative 5. And this is going to be X squared divided by 0.75 minus X. So here, what I'm going to do, you can try it by leaving this X there. But since this is a very weak acid, its Ka value is very small, 1.8 times 10 to the power negative 5, meaning that this X is also going to be very small. So ignore, it is small compared to 0.75 because 0.75 is much greater than this X. But you can also leave it there and do your calculation and you'll tell me what you'll get. So we are going to have 1.8 times 10 to the power negative 5, then is equal to X squared out of 0.75. So out of 1, and then X will be the square root of 0.75 times 1.8 times 10 to the power negative 5. Okay, so we take root of that. And the answer is going to be, so the X value here is equal to 3.67 times 10 to the power negative 3 m. So now we are asked to determine the pH of this solution. So to get the pH, we know this is the same as negative logarithm of the concentration of hydronium ions. We have the concentration of hydronium ions, which is X, but X is equivalent to 3.67 times 10 to the power negative 3. So this becomes negative logarithm of 3.67 times 10 to the power negative 3. And then our pH is giving us 2.43. So 2.43 is the pH of the solution. So this makes it acidic, since the pH is less than 7. Let's look at this problem. What is the pH of a 0.25 ammonia solution? Kb, that is the base dissociation constant, is 1.8 times 10 to the power negative 5. So we know ammonia also partially dissociates in water to form ammonium ions and hydroxide ions. So I'll get ammonia dissolved in water. I will form ammonium ions and hydroxide ions. So when we look at this, we are told that initially we are going to use ice tables. So let's put our concentration initially for ammonia is 0.25. This we don't count it because it doesn't contribute in the equilibrium reaction or in the equilibrium calculations. So what is here is 0 initially, and that is 0 initially. So what if we form X moles of hydroxide ions? We shall also have to form X moles of ammonium ions, and this is going to be minus X for ammonia solution. So at equilibrium, obviously that is the change. That is after when the reaction has taken place. If the dissociation occurs, then there is going to be a change in concentrations. We are going to be forming the ammonium ions because there is going to be a forward reaction. And then we shall also form hydroxide ions. Then at equilibrium, we have to add the two. That is what is available initially plus the change. Here this is a negative because it is reducing. And why negative X? Because the stoichiometric factor here is 1 for this, for that, and for that. If this was forming, for example, 2 hydroxide ions, then obviously we will multiply by 2 here to become negative 2. So add the 2 here, I'll have 0.25 minus X. Here I'll have X, here I'll have X. So we write the Kb, which is equal to the concentration of ammonium ions times the concentration of hydroxide ions divided by the concentration of ammonia solution. And this is equal to, at equilibrium, we are going to be taking, this is X, this is also X, and then at equilibrium, ammonia is 0.25 minus. So we know Kb as 1.8 times 10 to the power negative 5, so we'll have X squared, which is going to be equivalent to 1.8 times 10 to the power negative 5. We cross multiply here. So we'll have 0.25 minus X. But again, since Kb is small, this is a weak base. Therefore, we can neglect X because X is much, much smaller by 0.25. We have taken that assumption, but you can also leave it there and do the calculation. This will give you a quadratic equation. Go ahead and calculate, then you'll see if you don't get a value slightly equivalent to what we are going to get here. So this X will be the square root of 1.8 times 10 to the power negative 5, then times, and then this gives us X equivalent to 2.12 times 10 to the power negative 3. This is molar or moles per liter. Since X is equivalent to that value, then we have the concentration of hydroxide ions because it is also equivalent. So to get the pH, we can get the pOH, which will be negative logarithm of the concentration of hydroxide ions. This is negative logarithm of 2.12 times 10 to the power negative 3. pOH is giving us a value that is equivalent to 0.67. But we know pH is equal to 14 minus pOH. That is at 25 degrees Celsius. This is 14 minus 2.67, and then our pH is equal to 11.33, and the solution is basic. Another problem, what is the pH of 0.40 molar of ammonium chloride solution? And then Kb of ammonia is 1.8 times 10 power negative 5. So we know that ammonium chloride, this is an ionic compound. So it is going to dissociate as follows. This is going to give us ammonium ions and chloride ions. But ammonium ions is a weak acid. This ammonium ion is a weak acid. So it is going to further dissociate in water to form ammonia solution and the hydronium ions. So what we are doing here, we have to know that this ammonium ion is a proton donor, while water is a proton acceptor. So water accepts this proton and becomes, or it forms hydronium ions. Then this releases its proton to form ammonia solution. We can write down the equation for reaction of ammonia solution, ammonium ions and water, forming ammonia solution and hydronium ions. So here we are going to use Ka, not Kb, because we see that ammonium chloride solution is acidic. Of course, we are talking about a weak acid. So therefore, having understood that, we are going to be using ICE. So what is the concentration of ammonium ions here? Initially, we are given that we have 0.4. We have 0.4. And then we also had 0 of ammonia and 0 of hydronium ions initially. But once the dissociation has occurred and the reaction is at equilibrium, then we are going to have what? We are going to have X here. X hydronium ions are going to form, then X moles of ammonia, and then minus X moles of ammonium ion. So at equilibrium, we are going to add the two. I'll have 0.4 minus X. This is X, and this is X. So Ka will equal to the concentration of hydronium ions, the concentration of ammonia solution, divided by the concentration of ammonium ions. But what is Ka? We know Kb times Ka is equal to Kw. So Kb, we already have it as 1.8 times 10 power negative 5. What is Ka? And this Kw is 1 times 10 power negative 14 at 25 degrees Celsius. So Ka will equal to 1 times 10 power negative 14 divided by Kb, which is 1.8 times 10 power negative 5. This is giving me 5.56 times 10 to power negative 10. So do I know the concentrations of hydronium ions and ammonia at equilibrium? Yes, we have X, and then for ammonium, we have 0.4 minus. So I'll have 5.56 times 10 power negative 10 equivalent to X times X divided by 0.4 minus. So again, we can see that Ka is very small, and therefore X is much smaller than 0.4. So we can neglect it. So neglect X at the denominator, meaning I'll have X squared divided by 0.4 is equal to 5.56 times 10 power negative 10. And out of 1, we cross multiply. So our X will be the square root of 5.56 times 10 power negative 10 times 0.4. So X will be 1.49 times 10 power negative 5. This is in terms of moles. So X represents the concentration of hydronium ions, and pH we know is equal to negative log of the concentration of hydronium ions, and this is negative logarithm of what? The concentration is 1.49 times 10 power negative 5. So finally pH is equal to 4.83, and this gives you an acidic solution because pH is less than 7. What is the pH of 1.5 molar sodium fluoride solution? The acid dissociation coefficient of hydrofluoric acid is 7.2 times 10 to power negative 4. Now, how do we determine the pH of such a solution? We know that the fluoride ion is base enough to change the pH of the solution. Therefore, I'll have the fluoride ion in water giving me hydrofluoric acid and the hydroxide ion. So it is this hydroxide ion that is going to help us determine the pH of this solution. So what does this mean? I need to write initially and at equilibrium. So initially, what is the solution molarity for sodium fluoride? So we have 1.5 moles. And for hydrofluoric acid, because initially the reaction hasn't taken place, this is going to be 0. And we shall find that since we have 0 of hydroxide ions and the hydrofluoric acid, then the reaction has to take place in the forward direction, meaning we are going to have a change in after some time we have a change in the number of moles or concentration for hydroxide and for this HF. So let us assume that the change is X here, and according to the stoichiometric ratio, also this will give us X moles. And what does that mean? For the fluoride ions, they will reduce by negative X according to the stoichiometric ratio. So if I add the two at equilibrium, I'll have the concentration. So at equilibrium, I'll have 1.5 minus X for the fluoride ion. I'll have X of the HF. I'll have X of the hydroxide ion. Meaning, I'm going to write down Kb because I'm dealing with a base or a basic component. Because we said if this is a solution of sodium fluoride, and we said that the fluoride ion is base enough to change the pH, then I'm going to be using Kb. Yes, I'm going to be using Kb, and then I'll be able to determine the pH of the solution. So what is the Kb? I'll have the concentration of the hydroxide ions. What is Kb? Kb will be the concentration of hydroxide ions, and then the concentration of HF divided by the concentration of the fluoride ions. And I'm going to use the equilibrium concentrations. For this, we have X for HF, and then for the fluoride ions, we have 1.5 minus X. Remember, we are given Ka for HF. So how do we determine Kb? We know that Ka times Kb is equal to Kw. So therefore, Kb will be Kw divided by Kb, and this is 1 times 10 power negative 14, that is at 25 degrees Celsius, divided by Ka, which is given as 7.2 times 10 power negative 4. This is 1.39 times 10 power negative 11. 1.39 times 10 power negative 11 is equal to x squared divided by 1.5 minus x. So since Kb is small, it's very small, then x is going to be much smaller than 1.5. And therefore this x can be neglected. Try to include it in your separate calculation. You will see that it almost becomes insignificant when we are subtracting it from 1.5. So therefore x squared will equal to, I put this out of 1 and I cross multiply. So I'll have 1.39 times 10 power negative 11 times 1.5. So x will equal to, if I take the square root of that, then I will have 4.566 times 10 power negative 6, and this is in number of moles per liter. So meaning, since we have the concentration of the hydroxide ions, I can get the power of hydroxide ions, which is negative logarithm of the concentration of hydroxide ion. This will equal to negative logarithm of 4.566 times 10 power negative 6, and this gives us 5.34. So pH for the power of hydrogen ions will be 14 minus 5.34, giving us 8.6. Therefore, it confirms to us that the solution is alkaline stroke basic.